Welcome to our lesson on Taylor expansions in one variable. Taylor series are powerful tools in calculus that allow us to approximate complex functions using polynomial expressions. A Taylor series is essentially a way to represent a function as an infinite sum of terms calculated from the values of the function's derivatives at a single point. Let's start by understanding the goal of a Taylor expansion. Our goal is to approximate a function f of x by a sum of terms involving the derivatives of f at a specific point a. Mathematically, we write this as f of x is approximately equal to the sum from n equals 0 to capital N of the nth derivative of f at a divided by n factorial multiplied by x minus a raised to the power of n. Here, capital N represents the desired order of our approximation. The higher the order, the more accurate our approximation will generally be. Let's break down the process step by step. Step 1. Compute derivatives at the center point a. We need to calculate the zeroth derivative, which is just f of a, the first derivative f prime of, the second derivative f double prime of a, and so on up to the nth derivative. We use the notation f superscript n in parentheses of a to denote the nth derivative of f evaluated at a. Step 2. Form the general nth term of our Taylor expansion. The coefficient of x minus a raised to the power n is the nth derivative of f at a divided by n factorial. This structure captures how the function changes as we move away from the center point a. The factorial in the denominator helps control the growth of the terms as n increases. Step 3. Write the finite Taylor polynomial of degree n. We denote this as t subscript n of x, which equals the sum from n equals 0 to n of the nth derivative of f at a divided by n factorial multiplied by x minus raised to the power of n. This is a truncated version of the infinite Taylor series, including only the first n plus 1 terms. Step 4. Consider the remainder or error term. The remainder after n terms in Lagrange's form is given by the n plus 1 th derivative of f at some point 11 between a and x divided by n plus 1 factorial multiplied by x minus raised to the power of n plus 1. If this remainder approaches 0 as n approaches infinity, then the infinite Taylor series converges to f(x). The remainder is crucial for understanding how accurate our approximation is. Let's see an example of Taylor expansion in action. We'll expand the exponential function e to the power of x around the point a equals 0. This special case is also called a Maclaurin series. First, we need to compute the derivatives of e to the x at the point a equals 0. The interesting property of the exponential function is that all its derivatives are equal to itself. So we have f of x equals e to the x, f prime of x equals e to the x, f double prime of x equals e to the x, and so on. When we evaluate these at x equals 0, we get f of 0 equals e to the power of 0, which is 1, f prime of 0 equals e to the power of 0, which is also 1, f double prime of 0 equals e to the power of 0, which is still 1, and so on. All derivatives at 0 equal 1. Now we can form the Taylor series for e to the x around 0. We get e to the x equals the sum from n equals 0 to infinity of x to the power of n divided by n factorial. Written out, this becomes e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. Let's visualize how this series approximates the exponential function as we include more terms. Let's summarize the procedure for finding a Taylor expansion. Step 1. Choose a center point a. Step 2. Compute all needed derivatives f to the n of a. Step 3. Form the terms f to the n of a divided by n factorial times x minus a to the power of n. Step 4. Sum up to the desired order n, or to infinity if the series converges. Step 5. Optionally, estimate the remainder term to understand the approximation error. In conclusion, Taylor expansions provide us with a powerful way to approximate functions using polynomials based on the behavior of the function at a single point. These approximations are incredibly useful in various areas of mathematics, physics, and engineering, from numerical methods and computational algorithms to solving differential equations and analyzing functions. With practice, you'll be able to find Taylor expansions for many common functions and use them to solve complex problems. Thank you for watching.